Previously, we looked at giving more flexibility to our modeling with the k-nearest neighbors algorithm for regression. In this video, we'll look at how our familiar linear regression models can be extended in order to model nonlinear trends. As the data here show, it's useful to us in building machine learning models to be able to model nonlinear trends. We've seen how a non-parametric method, KNN regression, was able to learn nonlinear functions naturally due to its flexible assumption that cases with similar predictors should have similar responses. It turns out that parametric linear regression models, when suitably extended and generalized, can handle nonlinear trends as well. We'll explore these tools in this video. One technique that fits exactly into the linear regression framework is polynomial regression. In polynomial regression, we use polynomial terms for a predictor in a linear regression model. For example, instead of a line model given at the top, we use the model at the bottom, where x is represented by a degree 3 polynomial. Computationally, this requires adding transformations of the original variable as new predictors in the model. We create these transformations by squaring and cubing the x predictor. These new predictors are then treated just as regular variables in ordinary least squares linear regression. The plot on the right here shows the trend predicted by models with up to a degree 2 polynomial in orange and up to a degree 3 polynomial term in blue. The trends are slightly different, but both capture the nonlinear trend better than the simple linear regression model at the top, which would just model a straight line. Polynomial regression certainly gives us the flexibility to model nonlinear relationships, but the drawback is that it imposes a global structure on the relationship between the predictor and the response. What do we mean by global structure? For example, if we use a degree 3 polynomial for the predictor, this global structure is saying that the relationship looks cubic over the entire range of x, from 0 to 6. This can be limiting if, for example, the relationship looks cubic from 0 to 3 and linear from 3 to 6. So we can ask, is there a way to make polynomials in pieces? We actually can. Let's look at the idea of piecewise polynomials. Instead of fitting a polynomial globally over the entire range of x, we fit several different polynomials locally in different regions of x. In the example shown here, wages are modeled as a nonlinear function of age with two piecewise polynomials. A degree 3 polynomial with one set of coefficients is used for the region of age less than 50. A second degree 3 polynomial with another set of coefficients is used when age is greater than or equal to 50. And to this point at age equals 50, where the coefficients for the polynomial terms change, is called a knot. A problem that we can immediately notice is that the function looks unnatural. There's a discontinuity, a jump, at the knot that is probably not a great model for how wage actually varies with age in real life. These discontinuities make piecewise polynomials undesirable for modeling. But it turns out that piecewise polynomials can be rescued with the help of mathematical constraints that enforce qualities of smoothness at the knots. Mathematical constraints can force the piecewise polynomials to be continuous and have continuous first and second derivatives at the knots. Having continuous first and second derivatives means that the function will have continuous slopes and continuous slope of slopes. The functions that arise are called cubic splines. This second plot attempts to fix the discontinuity of the piecewise polynomial shown on the left, but it has only been constrained to be continuous at the knot, not necessarily to have continuous first and second derivatives. It looks better than the first plot because it's continuous at the knot, but it still looks a bit odd in that the slope, the first derivative, changes suddenly. The slope switches immediately from negative on the left to positive on the right. This is why it's desirable to have continuity in the first and second derivatives as well. The last plot on the right shows a function that was constrained to be continuous at the knot and have continuous first and second derivatives. It looks quite smooth and still generally seems to fit the data well. This function is a cubic spline. One problem that arises with cubic splines is that in the boundary regions, which are the regions lower than the smallest knot and higher than the largest knot, cubic splines can be highly variable. In other words, we have much higher uncertainty in the function estimate in these regions. In technical terms, this results in higher standard errors for the predicted values in these boundary regions. In this figure, the solid blue trend line is a cubic spline model of the wage versus age relationship. The dashed blue lines give the confidence interval for the predicted values as a function of age. And we can see that in these boundary regions, these bands are quite wide, indicating that the predictions from the cubic spline are highly uncertain in this region. A small modification of the cubic spline is called the natural cubic spline. Natural cubic splines impose the constraint that polynomials are linear in the boundary regions. We see from the confidence interval bands that natural cubic splines have lower variability in the boundary regions. Natural cubic splines are a very popular tool for nonlinear modeling for their flexibility in handling many sorts of nonlinearity. We've described conceptually what splines are and how they're better versions of piecewise polynomials, but how do we actually construct them? How do we actually represent them mathematically? What's happening behind the scenes when we use them in models? Recall that in polynomial regression, we model a global nonlinear trend, a global polynomial trend, for a particular variable by including new transformed versions of the original variable. These transformations are the raising of the predictor to different powers. Here, we want to model a global cubic polynomial trend for the x variable. So in addition to the linear x term, we also include an x squared and an x cubed term. The key idea is that including several transformations of the variable allowed us to model the desired nonlinear trend. We similarly use a set of variable transformations when we use splines in regression models. However, instead of simple power transformations of the predictors, more complex polynomial functions are used for transforming the predictors. We won't display the form for these polynomial functions because they're pretty long, but the key idea is that the combination, in particular the linear combination, of these complex polynomial transformations succeeds in creating a natural cubic spline function of the x predictor variable. A function of x that is composed of piecewise polynomials, which is to model local rather than global nonlinearity, that are continuous up to the second derivative, which is to ensure a smooth-looking function, and linear in the boundary regions, which is to reduce variability and estimation at the extremes. Let's look at a visual representation of these complex polynomial transformations. Let's visually inspect what went into making the red natural cubic spline fit for the age predictor. It turns out that for 3 knots, 3 cut points, which are located at ages 25, 40, and 60, we needed 4 transformations, which are indicated by F1 through F4 in the model statement at the top. These 4 transformation functions are shown at the right. For example, for a case whose age is 30 years, we would fill in their value for the 4 new variables by looking up the function value at age equals 30 for each of these 4 transformation functions. We do this for all cases to fully define the 4 new transformed predictors, and we'd use these new variables in ordinary least squares regression to estimate the best values for beta 1 through beta 4. In summary, natural cubic splines are a flexible and popular way to handle nonlinearity. They allow us to model nonlinear trends piece by piece across regions of a predictor, which is an improvement over polynomial regression, which assumes that a particular polynomial trend holds across the entire span of a predictor. Natural cubic splines also look smooth, which is in contrast to piecewise polynomials. This is likely more realistically capturing the true underlying nonlinear trends in the data. Finally, they also fit nicely within the linear regression framework. Least squares is a computationally stable and convenient framework, so it's nice to be able to still model nonlinearity by just employing variable transformations.